On November 11, 1956, a machine rose into the sky over Texas that looked like an alien from a distant future. Convair B-58 Hustler, the first production supersonic bomber, capable of flying twice the speed of sound and becoming a real challenge to the laws of physics. How did engineers manage to solve the problem of saving the crew at speeds over 2,000 kilometers per hour, locking the pilots in individual space capsules? Why did a machine made of advanced honeycomb panels, equipped with the first voice assistant, turn out to be astronomically expensive and frighteningly dangerous to operate? What threat did the high landing gear of this Titan pose, and why did its revolutionary concept become obsolete immediately after entering service? Watch the video to the end. Today we will disassemble the mysteries of the B-58's construction and find out what price had to be paid for this technological breakthrough. Let's begin. The autumn of 1951. In the offices of the Convair Company in San Diego, engineers receive a document that at first glance looks like a clerical error. The United States Air Force formulates a requirement under the code designation SAB-51. The meaning of the document is simple, and at the same time almost absurd for its time. The new bomber must cover key sections of the route at a speed 2.1 times the speed of sound, and do this at an altitude of over 16 kilometers. For 1951, this is not a technical specification. This is a challenge thrown at the very laws of aerodynamics. Not a single production aircraft in the world, then, flew so fast at such an altitude. Jet aviation was only just getting rid of its teething problems. Convair, however, had one trump card. A few years earlier, they built an experimental interceptor under the designation XF-92A. It was this machine that was the first in the United States to prove that a delta-wing, tailless design works not only in a wind tunnel, but also in the real sky. A man named Robert Widmer led the new task, a person for whom calculations at the limit of material strength were a normal working environment and not a cause for alarm. A dilemma familiar to any designer of supersonic technology stood before his group. Speed and flight range almost always contradict each other. The faster an aircraft flies, the more fuel it burns for every kilometer traveled. And the customer demanded not just speed. The customer demanded speed combined with intercontinental range, two characteristics that engineers were used to considering mutually exclusive. Widmer's team went through dozens of options for wing shape and fuselage layout. Almost every sketch was checked, calculated, and sent to the trash. In the end, a solution was born that looked almost elegant on tracing paper. A delta wing with a sweep angle of 60 degrees. This shape sharply reduced wave drag precisely at supersonic speeds, where a conventional straight or moderately swept wing begins to slow down the aircraft with the mass of its own air. And the huge area of such a wing at the same time solved the second problem. It provided the volume for placing fuel, which was catastrophically lacking in previous sketches. One wing shape and two solutions for the two main problems of the aircraft at once. But any truly bold solution has a hidden price, and Widmer's team had to pay this price very soon, and in a literal sense, at the cost of the very existence of their project. While the contours of the future bomber were being born on the drawing boards, no one in the company suspected one thing. Almost 10 years remained until the production of this machine, and on this path, the program would be placed on the verge of complete closure more than once, and the first blow would come from where it was least expected. The first serious blow to the future bomber was delivered not by generals and not by budget commissions. It was delivered by the engines themselves. Initially, Convair engineers planned to place the power plant in twin nacelles, two engines and one streamlined pod under each wing console. The scheme looked logical: fewer individual structural elements, fewer extra surfaces creating drag. Reality proved far more brutal. Blowdowns in the wind tunnel showed that at transonic speeds, that is, at the moment when the aircraft is only approaching the speed of sound, air resistance does not increase by percentages. It increases several times over. For a machine that had to stably hold a speed twice the speed of sound, such a jump meant one thing: the project in its current form simply could not achieve the required characteristics. The solution was not found immediately. The key was the discovery by American engineer Richard Whitcomb, the so-called area rule. If you plot the cross-sectional area of an aircraft along its entire length, ideally this graph should be smooth, without sharp jumps. Much like the silhouette of a bottle rather than the silhouette of a ladder. The twin nacelles created just such a sharp jump in area, precisely where the wing ended and the engines began. The solution proved elegant on paper and laborious in practice. 4 J79-GE-5 engines were separated into individual nacelles, suspended at some distance from each other under each wing console. The longitudinal section of the aircraft leveled out, drag decreased, but time was lost, and with it the patience of the customer. By 1955, after another series of tests of scale models, the engineers received a result that chilled even the most optimistic participants in the program. The calculated flight range turned out to be significantly lower than what the technical specification required. For a bomber designed for intercontinental distances, this was almost a death sentence. What was the point of an aircraft flying twice the speed of sound if there was only enough fuel for part of the required route? The forces, who had been watching the program for several years, began to lose interest seriously. Budgets are not elastic, and a troubled machine is too risky a bet against the background of production aircraft already flying. The result was not long in coming. The program was transferred to the status of a purely experimental topic. Formally, this meant one thing: just enough funds to fly the remaining test flights and not a cent more. Convair engineers found themselves in limbo. A machine in which several years of work had been invested risked remaining a beautiful but forgotten exhibit in the history of aviation. But sometimes the fate of an aircraft is decided not by engineers and not by generals at the negotiating table. Sometimes it is decided by an event that occurs in a completely different place and for a completely different reason, an event to which the project under threat of closure had no direct relation. The answer to the riddle turned out to be simple and almost ironic. The program was saved not by the flight data of the bomber itself, but by anxiety of a completely different kind, anxiety for the fate of aircraft already in service. By the late 1950s, the Strategic Air Command of the United States was looking more and more closely at its own fleet of equipment. The basis of long-range strike aviation then consisted of B-47 Stratojet bombers, machines that only recently seemed the pinnacle of progress. The problem was not that these aircraft suddenly broke down or became physically obsolete. The problem was the calendar. Air defense systems in the world were developing much faster than the designers of the B-47 had assumed just a decade earlier. The command understood a simple thing: the longer the replacement of the aging fleet was postponed, the higher the risk of one day being left with equipment that physically could not perform the assigned task. And then, a half-forgotten project came back into view: the very same Delta Wing aircraft that had been gathering dust in the status of an experimental topic for several years. The irony of history is that by this time the machine had already been flying for a long time. The first flight of the prototype took place back in 1956, 3 years before the command seriously thought about its fate. For 3 years, the aircraft took to the air, gathered statistics, returned for revision, flew again, but formally remained only an expensive research topic and not a production machine. In early 1959, the situation changed. The command decided to return the program to the status of a production development. Convair received an order it had not expected for several years. But it is one thing to make a decision on production, and quite another to bring the first full-fledged aircraft to an active unit. Between the decision and the result, time passed again. Only on August 1, 1960, did the first truly production specimen enter service. Almost 4 years passed from the first flight of the prototype to this moment. 4 years of testing, revisions, and training of technical personnel to work with a machine unlike anything that before it had stood in service with the United States Air Force. By this time, the aircraft already had an official name: Hustler, a name that the whole world would soon know. But for now, only a few engineers and test pilots knew it, daily checking the very idea of flight at the limit of physics. But to understand why the creation of this machine stretched over so many years, one must look deeper, not into the history of decisions and orders, but into the construction of the aircraft itself, to where the engineers had to solve tasks that no one before them had faced. On the drawings of the Hustler, it is difficult to understand at first glance where the fuselage ends and the wing begins. And this is not a coincidence of the artist, but a deliberate engineering decision. A conventional aircraft is arranged like a train of individual modules. The fuselage is separate, the wing is separate, connected to each other by fasteners and joints. On the Hustler, the designers went a different way. The structural elements of the fuselage actually transitioned into the structural elements of the wing, forming an almost monolithic structure. 33 spars ran inside this structure, longitudinal load-bearing beams on which the entire rigidity of the airframe rests. For comparison, most of its contemporary aircraft had several times fewer of them. Such a number of spars was not a whim of the engineers. It was a direct response to the loads arising during flight at a speed twice the speed of sound, when every gust of air strikes the skin with a force unthinkable for the aviation of the previous decade. The engineers of that time well understood the price of an error in such calculations. The destruction of a wing at such a speed leaves no time for correction. The count goes to fractions of a second and not to minutes, as in the flight of a conventional piston aircraft of previous decades. But there was a downside to the strength of the structure, and this is the second key detail of the Hustler's wing. The wing profile was made exceptionally thin. A thin profile sharply reduces air resistance at supersonic speeds. The thicker the wing, the more it trips over the air when accelerating past the speed of sound. Engineers knew this very well. They also knew the other side of the coin. A thin wing is a wing with less margin of safety, less internal space for structural elements, less material capable of taking the load. Take a regular sheet of paper, thin and flexible on its own, but if you fold it into an accordion, it holds a weight unavailable to a flat sheet. Much the same logic was hidden in the wing of the Hustler, only instead of paper there was metal, and instead of an accordion there were dozens of thoughtful structural elements. And here a question arises that stood before Widmer's team all these years of development. How to keep the shape of such a thin wing at twice the speed of sound without destroying it in the process? The answer was not in one decision, but in a whole series of technologies developed practically from scratch specifically for this aircraft. The spars discussed above are only part of the answer. No less important was the material of the skin itself covering these structural elements. Ordinary metal sheets used on most aircraft of that time were simply not suitable here. Too heavy for a thin wing, too vulnerable to new types of loads arising during long-term flight at such speeds. Convair designers had to turn to a material that no production aircraft in the world had used in such volumes before. This material turned out to be not metal in the usual sense of the word, but a real technological bet on the future. A bet that before the Hustler, no production aircraft had made in such volumes. About 80% of the Hustler's outer skin consisted not of solid metal sheets, but of 3-layer honeycomb panels, thin outer layers between which a light cellular filler was placed, resembling honeycombs in structure. In the zones of greatest heating, where friction against the air at supersonic speed heats the skin most of all, duralumin sandwiches were used. In other places, engineers used fiberglass, a material ideally suited where heating was not so critical, but other thermal insulation properties were important. The assembly of such panels was an almost human-scale jewelry task. The layers were glued with special epoxy phenolic compounds, and then additionally fastened with rivets made of steel or titanium, metals capable of withstanding the vibration and temperature changes of long-term supersonic flight. Why complicate the aircraft's skin so much in the first place? The answer is hidden in several planes at once. First, weight. A honeycomb structure with the same strength weighs significantly less than a solid metal sheet. And for an aircraft fighting for every extra kilometer of flight range, the weight savings on the skin were measured not in grams, but in hundreds of kilograms of fuel that could be taken additionally. Second, the surface. Honeycomb panels made it possible to achieve an exceptionally smooth and even skin, without dents, joints, and irregularities that seem like a trifle at subsonic speeds, but at twice the speed of sound turn into a source of extra turbulence and drag. And third, the most dangerous thing, protection against a phenomenon that engineers call panel flutter. This is the moment when the skin of an aircraft, under the action of airflow, begins to vibrate finely, and then this vibration grows like an avalanche, literally destroying the metal in a matter of seconds. Rigid honeycomb panels are much more resistant to such behavior than thin, solid sheets of metal. For a machine that was to fly for years at the limit of speed, resistance to flutter was not a pleasant bonus, but a condition for the survival of the entire structure. One peeling or weakened panel at such a speed could turn into a chain reaction of destruction in a matter of moments. The material solved the problem of weight, strength, and aerodynamics of the wing and fuselage practically in one fell swoop. But while the designers were celebrating victory over one engineering puzzle, a completely different problem awaited them below, literally under the belly of the aircraft, one much more down to earth in the most direct sense of the word. A large capacity container was hidden under the Hustler's fuselage, and it was this container that dictated one of the most unusual features of the entire machine. In order for this container to fit between the ground and the belly of the aircraft during takeoff and landing, the landing gear had to be made unexpectedly high. The height of the struts dragged with it a whole chain of difficulties. The main landing gear struts carried 8 wheels each, a whole bogie, and not the usual pair like most bombers of that time. When retracting the landing gear, these bogies turned 90 degrees and hid in the root parts of the wing. The niches for them turned out to be so large that they protruded beyond the usual contour of the wing. They had to be covered with separate fairings so as not to spoil the already temperamental aerodynamics of the machine. It seemed to the engineers that the most difficult task was to hide these bulky bogies in the body of the aircraft. But the real problem was waiting not in the air, but on the concrete of the runway. It was about the tires. During takeoff, and especially when landing at high speeds, the Hustler's tires showed a tendency to burst, a phenomenon that the aviation of those years had not yet really encountered. Not a single production aircraft had ever touched the ground at such speeds before. The payment for this flaw came in 1960. A tire burst during one of the flights led to a disaster that cost the lives of 2 crew members, a reminder that every detail in this aircraft worked at the limit of its capabilities, and any weakness turned into a real threat. The answer followed quickly, for the aircraft industry of that time at any rate. Already in 1961, additional emergency wheels were installed between the main wheels of each bogie. The logic was simple and in its own way severe. If the main tire bursts, the emergency wheel does not allow the fuselage or elements of the bogie to touch the concrete of the runway at a speed at which this would destroy the structure of the aircraft. A small detail added after the fact was a direct response to an event that the designers did not foresee at the design stage. The history of the Hustler's landing gear is perhaps the most vivid reminder that when working at the limit of technology's capabilities, the price of an error is measured not only in money, and not only in time for revision. But if metal and rubber faced loads at the limit of strength, what was it like for the people who sat inside this machine and controlled it during multi-hour flights at a speed inaccessible to the understanding of most passengers of conventional airlines of that time? The Hustler crew consisted of only 3 people: a pilot, a navigator, and a defense systems operator. The 3 had to control a machine working at the limit of metal capabilities and at the same time remain safe in conditions close to space. At a speed of 2,124 kilometers per hour, conventional ejection turned into an extremely risky undertaking. The force of the oncoming airflow at such a speed is capable of causing severe injuries to the human body. A simple seat with a parachute, thrown into such a flow, made it practically impossible for the pilot to survive the ejection process itself, let alone a safe landing. A solution was required that was as radical as it was effective. Each crew member was located in his own sealed capsule, an individual protective shell with an autonomous life support system and a soft, shock-absorbing bed inside. In an emergency, the capsule ejected with the person as a whole and not separately from him, as in the case of a conventional seat. After separating from the aircraft, it stabilized in the air and then opened its own parachute, lowering it to the ground already gently and predictably. Each of the 3 crew members had to fully trust this design, knowing that the survival depended on the proper operation of dozens of mechanical and pyrotechnic elements, and not just the comfort of the flight, but the very fact of whether they would ever step on the ground again. This was one of the first production escape systems of this type in the world, and it more than proved its worth. Over the years of operation, the Hustler capsules more than once saved the life and health of the crew in critical situations, including accidents at low altitude, where there was practically no time left for decision-making. The engineers who came up with this system solved a task that no one in world aviation had solved on such a scale before them: how to save a person from a speed at which the air itself behaves not like a familiar environment, but almost like a solid wall. The answer turned out to be workable, and this is perhaps one of the most human engineering solutions in the entire history of the Hustler. A machine built for the sake of ultimate speed did not forget about those who sat inside it. But safely leaving a falling machine is only half the task of survival. Far more often, the crew had not to escape, but to control, to hold a multi-ton aircraft on course, at speed, and at altitude, where conventional ideas about piloting stopped working. And here, another system came to the rescue of the pilot, almost as revolutionary as the escape capsule itself. At high speeds and altitudes, manual control of the Hustler became almost impossible. Human reactions simply did not keep up with the processes occurring around the aircraft at twice the speed of sound, where a second of delay means kilometers of untraveled path in the wrong direction. Therefore, the Hustler was equipped with a booster, irreversible control system, and a duplicated one at that. Irreversible meant that the pilot's efforts on the control column were not transmitted directly to the control surfaces, but only set the command to the hydraulic actuators, which themselves moved the flaps, ailerons, and rudders. Duplication meant a redundant circuit in case of failure of the main one. At such a speed and altitude, a failure of the control system left no time for improvisation. But the real brain of the aircraft was the autopilot, which received the designation AN/ASQ-42. For its time, this device was almost fantastic. The autopilot held course, controlled the Mach number, monitored altitude, and performed complex navigation tasks. Moreover, it relied on several independent data sources at once: an inertial navigation system, an astronavigation system oriented by the position of the stars, and a Doppler system that measured the aircraft's drift relative to the ground by changing the frequency of the reflected radio signal. 3 independent ways to understand where the aircraft is located is not a luxury, but a conscious redundancy. On an intercontinental route, far from ground radio beacons, an error in determining the location could cost the crew many hours of flight and tons of precious fuel. However, the most unexpected feature of the autopilot was not navigation accuracy, but the way it communicated with the crew. In addition to the usual light indicators and alarm sounds, the system informed the pilots about 20 different types of emergency situations, and did so with a female voice. For the late 1950s and early 1960s, this was a real technical curiosity. Synthesized speech on board an aircraft was one of the earliest examples of such a solution in all of world aviation, many years before electronic voices became a familiar part of the cockpits of modern airliners and car interiors. The engineers were guided by simple logic. Under stress and overload, the human brain reacts faster to meaningful speech than to another flashing indicator among dozens of others on the instrument panel. A voice pronouncing a specific phrase about a specific problem saved precious seconds, and at the speed of the Hustler, seconds meant a lot. All this advanced electronics, however, was not created for its own sake. Every device, every navigation and communication system existed for the sake of one single task, and this task was arranged extremely unusually compared to most bombers of that time. Most bombers of that era had a common feature: a spacious compartment inside the fuselage, where the payload was placed and securely hidden from the oncoming airflow. The Hustler had no such compartment at all, and at first glance this seems strange for a machine created for the sake of a single task. The designers consciously abandoned the classical solution. The reason is simple. Any internal compartment is a gap in the power scheme of the fuselage, additional weight of doors and mechanisms, and also volume that has to be carved out at the expense of fuel in an already cramped hull. Instead, Convair engineers placed one large suspended container of a combined type under the fuselage. This container performed 2 functions at once. It served as both a fuel tank and a holder for a thermonuclear payload at the same time. The solution was, in its own way, elegant. One node instead of 2 separate systems. One streamlined body instead of several protruding elements, spoiling the aerodynamics of the machine. The first such container was the apparatus under the designation MB-1C. Inside, it was a powerful thermonuclear payload, known under the index W39Y1-1. On paper, everything looked logical. In practice, an unpleasant surprise awaited the designers, which, apparently, was not thought of immediately. This container, in addition to the payload, carried a solid supply of fuel for a long flight. But fuel, unlike payload, is consumed during the flight. And here a question arises, not so obvious at the stage of drawings. What happens to the container after the fuel in it runs out? The answer turned out to be unpleasant. The empty container did not disappear and did not separate from the aircraft on its own. It remained hanging under the fuselage, a huge, already useless piece of metal, creating only aerodynamic drag and giving the aircraft absolutely nothing in return. Every extra percent of aerodynamic drag meant less distance traveled, less radius of action, less of the very intercontinental scope for which this whole aircraft was originally intended. It turned out to be an almost paradoxical situation. The container, designed to increase range with extra fuel, began to work against the same range in the second half of the flight, literally eating up the remains of the radius of action with its own resistance. Convair engineers, of course, noticed this problem quickly enough. A container eating itself with aerodynamic drag was hard not to notice during the very first test flights. The question was only whether it would be possible to solve it without redesigning the entire concept of the container from scratch. A partial solution to the problem was found quickly enough. The single container was replaced by a two-component container under the designation TCP. It was arranged more cleverly than its predecessor. The lower part was a large fuel tank that could be dropped immediately after fuel depletion, freeing the aircraft from extra drag. The upper part was a smaller component with a thermonuclear payload, designated with the index W-53, which remained on the aircraft until the very completion of the task. The logic was simple and in its own way beautiful. The empty tank no longer hung as a dead weight under the fuselage. It simply separated and fell down, and the compact payload component continued the flight together with the aircraft, creating significantly less drag than the previous bulky one-piece container. The problem of resistance after fuel depletion retreated. But the leadership had a new idea that again changed the whole picture. One payload for one target seemed not enough to the command. They wanted more yield from each Hustler flight, the ability to hit not one, but several targets in one flight. Therefore, all production Hustlers underwent modification. Under the root parts of the wing, long power beams with 4 additional holders were installed. Now the aircraft could carry not one, but 5 payloads at the same time, 1 in a suspended container, and 4 Mk-43 bombs attached to the new pylons. It sounds like a clear strengthening of capabilities, and on paper it was so. But any additional node under the wing has its aerodynamic price, and in the case of the Hustler, this price turned out to be much higher than expected. 4 additional bombs on open pylons are 4 new sources of air resistance, and precisely where the aerodynamics of the aircraft were already honed literally to the millimeter, drag increased sharply. And along with it fell the very indicator for which this whole aircraft was originally intended, the radius of action at supersonic speed. The figure turned out to be almost symbolic, 800 kilometers. That was all the aircraft could count on, designed as an intercontinental strategic carrier of a thermonuclear payload, capable of working at distances of thousands, not hundreds of kilometers. The machine, for the sake of which a whole technological revolution was built, from the delta wing to the escape capsules and the electronic autopilot, in this configuration actually turned into a tactical carrier with an extremely limited range of action, a paradox familiar to engineers at all times. The more load you try to cram into an ideally tuned structure, the more it loses the very quality for which it was originally created. But if the offensive capabilities of the Hustler come at such a price, it is natural to ask, how did this machine protect itself when left one-on-one with an opponent? The answer, strangely enough, was arranged extremely logically. The Hustler's defense was concentrated only in one direction, in the rear hemisphere. The designers did not consider the forward hemisphere vulnerable at all, relying on the fact that the speed and altitude of the flight itself reliably covered the aircraft from the front. The logic is in its own way understandable. Catching up with an aircraft flying twice the speed of sound at an altitude of almost 18 kilometers in the forehead is practically impossible. An interceptor simply will not have enough speed and energy for a frontal attack. It was much more realistic to expect pursuit from behind, after the Hustler passed over the target and began to withdraw. That is why in the tail part of the fuselage, in a special fairing, a turret with a 6-barrel 20mm gun under the designation M61 Vulcan was placed. The work of the turret was controlled by a separate radar station installed at the base of the keel, its own eyes for aiming at a target behind the aircraft. The ammunition capacity of 1,200 rounds allowed for short but dense bursts at a pursuing interceptor. Not an endless supply, but sufficient for several serious attempts. The calculation was simple. Not to destroy the opponent for sure, but to force him to turn away, disrupt the attack, and buy the aircraft a few precious seconds. Much more important than the gun, however, was a completely different defense system, invisible but much more effective. The Hustler's electronic countermeasure suite included a radar warning receiver designated AN/ALR-12 with 4 antennas providing all-around visibility of the space around the aircraft. As soon as the radar of an air defense system or an interceptor felt the Hustler with a beam, the system automatically reacted. It launched chaff, thin metal strips that confused the opponent's radar, from tin packages located in fairings on the wings. In addition to this, there were active jammers and countermeasures against heat-seeking missiles on board, a whole set of instruments invisible to the eye, working even before the crew had time to realize the scale of the threat. It looks impressive, a gun in the tail, invisible electronic protection, automation reacting faster than a human. But this whole defense system was built on one basic assumption that the engineers in command took for granted for years to come. The assumption was that the Hustler would fly high, where the radio horizon allows for detecting a threat in advance, dozens of seconds before real contact, leaving time for both maneuver and jamming. What if this assumption suddenly stops working? It stopped working faster than anyone in high offices calculated. And for this, it took not a decade of technological lag, but only a few years. On paper, the Hustler's characteristics still look stunning. Maximum speed 2,124 kilometers per hour, which corresponds to Mach 2. Service ceiling 18,105 meters. Ferry range 10,434 kilometers. 3 figures, each of which individually could decorate the advertising booklet of any aircraft manufacturer of those years. But the effectiveness of an aircraft is determined not only by its own characteristics, it is determined by the ratio of these characteristics with the capabilities of the opposite side. And here, everything changed abruptly. In the Soviet Union, the development and deployment of highly effective air defense missile systems capable of hitting targets at altitudes above 15 kilometers began. A few years ago, altitude was a reliable defense of the flight itself. 18,000 meters seemed practically unattainable for the air defense systems of that time, a distance for which a missile required time, accuracy, and engine power that had not previously existed in such a combination. The new missile systems wiped out this advantage in one fell swoop. The Strategic Air Command of the United States had to admit an unpleasant thing. The concept of high-altitude penetration, to rise above the zone of effective destruction and pass to the target at speed, became obsolete almost overnight, literally in the years after the Hustler entered service. The obvious question arose: what to do next with an aircraft whose entire construction was tailored precisely for high-altitude flight? The answer was found in a change of tactics. Instead of high-altitude penetration, they proposed using flight at extremely low altitudes, literally hugging the terrain, using hills and ridges as a natural shield from opponent radars. The idea is in its own way sound. A radar station physically cannot see through a mountain or a hill. This means that an aircraft flying at the very ground and hiding behind the terrain becomes a much less noticeable target than a machine going in a straight line at an altitude of 18 kilometers. A similar principle is used today. Modern low-profile cruise missiles use the terrain in exactly the same way as a natural cover from radar detection. The problem lay in another. The Hustler was not created for such a mode of flight at all, and very soon this would become noticeable to everyone who tried to apply the old machine to the new tactics. The Hustler airframe was designed for one specific flight mode: smooth, stable, at high altitude, where the air is calm and the overloads are minimal and predictable. The designers calculated the strength of each spar precisely for these conditions, and it was these calculations that once made it possible to create an incredibly light and slender structure. Flight at low altitude is a completely different physics. Air currents at the ground are turbulent. The terrain forces the aircraft to constantly maneuver, raise its nose, lower it, change course, reacting to every hill and ravine along the way. Each such maneuver creates an overload that the Hustler construction simply did not provide for. The airframe began to experience loads for which it was not originally calculated. This was especially true of the fatigue strength of the metal, the ability of the material to withstand repeated load cycles without gradual destruction of the structure. What accumulated over years in high-altitude flight could accumulate in a matter of months of operation near the ground. But the airframe was not the only victim of the change in tactics. The aircraft's electronics, All that advanced content of which the Hustler was rightfully proud just a few years ago also suffered no less. The autopilot, navigation blocks, communication and electronic defense systems were tightly packed into the fuselage, counting on a relatively calm high-altitude flight. Constant shaking and vibration at low altitude created exactly the conditions for which this electronics was never designed. Components that worked flawlessly at an altitude of 18 kilometers began to fail where the aircraft was thrown from side to side every few seconds of flight. Added to this was another, perhaps the most critical problem. The Hustler simply did not have a terrain-following radar, a system capable of automatically tracking altitude above the ground and warning the crew of an approaching obstacle long before visual contact. Without such a system, flight at extremely low altitude turned into a task requiring constant visual control of the terrain from the crew, and this at a speed at which the count to a collision with a hill or a high tree goes to seconds, not to minutes. Such a load on the eyes and attention of the crew was unthinkable for a multi-hour flight. While some Convair engineers tried to save the concept with targeted revisions, the headquarters of the Strategic Air Command were already preparing a completely different decision regarding the future of this aircraft. The year 1967 became the last serious attempt to breathe a second life into the Hustler. Several machines were modified to use conventional, non-nuclear bombs and sent for testing in an unusual role years after the aircraft was created for a completely different task. The idea was as follows. The Hustler, equipped with an advanced navigation system, could act as a kind of guide for a group of slower subsonic bombers, lead them precisely to the target while they themselves held formation behind. On paper, the plan looked reasonable. One fast and precise machine points the way to a whole group of less advanced aircraft. In practice, things did not go so smoothly. The AN/ASQ-42 autopilot, the very one that made such a strong impression at high altitude with its accuracy and abundance of functions, showed completely different results at low altitude. The navigation accuracy turned out to be unsatisfactory, precisely where jewelry work was required from it to lead a group of aircraft precisely to the target. In addition to navigation problems, another unpleasant reality was discovered. The very idea of group flight at supersonic speed and in difficult weather conditions turned out to be practically an impossible task for the technology and pilots of that time. To synchronize several machines going at different speeds in conditions of poor visibility and limited reliability of communication is a task that looked elegant in staff documents and turned into a real nightmare when trying to realize it in the real sky. The difference between the calculation on paper and the behavior of the technology in real conditions again turned out to be an abyss, and not a minor detail. The last straw was a case that clearly showed how poorly the new role suited the old machine. One of the Hustlers was damaged by fragments of its own dropped bomb, a situation unthinkable for an aircraft designed as an elegant high-altitude carrier of a single thermonuclear payload, and not as a machine for precision bombing at low altitude. This case became a decisive factor, finally putting an end to all further attempts at modification. The concept, which only a decade ago seemed an absolute technological breakthrough, could not adapt to the new realities of air defense, and no targeted revisions could change this anymore. The technical history of the project was drawing to its natural conclusion. But any ambitious program has another side, the bill that certainly had to be paid. That very landing gear screech with which this story began many years ago sounds quite different here. Not as a symbol of a technological breakthrough, but as a sound measuring the last months of service of a unique machine. The Hustler became one of the most expensive programs in the history of the United States Air Force. The final cost of the program reached $3.2 billion, in the prices of that time, of course. In terms of one aircraft, this turned out to be about $27.6 million per specimen. Critics of the time like to compare this sum with the cost of gold of equal weight. A sharp formulation, but close to the truth. The high price was not limited to the construction of the airframe alone. Hustler maintenance was extremely expensive, and training crews turned into a separate multi-year investment. A future pilot required at least 1,000 hours of flight time on jet aircraft before he was even allowed to fly the Hustler, and half of this 1,000 hours had to be spent precisely as an aircraft commander and not as a co-pilot. Add to this the training of ground technical personnel trained to work with the most complex electronics and unique skin materials, and the cost picture becomes truly impressive. But the most eloquent figure is the statistics of built and lost machines. A total of 116 specimens were built, 13 prototypes, 17 pre-production, and 86 full production machines. By the time of retirement in January 1970, 26 machines were irretrievably lost. Simple arithmetic gives a loss rate of about 22%. Almost every fifth built aircraft did not fly its days to the end. Such statistics speak for themselves. It points to the extreme complexity and danger of operating a machine working at the very limit of the technological capabilities of its time. Accidents occurred both at the testing stage and during ordinary service, and not only on the territory of the United States. Every lost machine meant not just written off millions of dollars, but another reminder that technology at the leading edge of progress is rarely truly safe. Two such cases occurred even across the ocean, at the Le Bourget airfield near Paris, where the Hustler was demonstrated to the public at international air shows, showing the whole world the capabilities of American supersonic engineering. But even being retired, this aircraft did not go straight to the museum hangar and was not forgotten forever. Several decommissioned Hustlers received a second life, not as strike machines, but in the role of flying laboratories, test platforms for technologies that still had to be brought to production use. One such aircraft, converted under the designation NB-58A, served as a testbed for the promising J93 GE3 engine manufactured by General Electric. This engine was being developed for another ambitious project, the XB-70 Valkyrie supersonic bomber, a machine even more extreme in its characteristics than the Hustler itself. Another decommissioned specimen became a platform for testing the fire control system under the designation AN/ASG-18 in conjunction with the AIM-47A missile, also known under the index GAR-9. None of these projects was brought to completion, precisely on the basis of the Hustler, but the tests conducted on board this already retired machine laid a direct technical foundation for one of the most recognizable carrier-based interceptor fighters in history, the F-14 Tomcat aircraft, armed with AIM-54 Phoenix missiles. It turns out to be an engineering chain beautiful in its own way. Technology born for one specific aircraft outlived its own service and migrated to a machine of a completely different class and purpose, a machine that determined the face of American carrier-based aviation for decades to come. It is worth remembering how this whole story began. In the autumn of 1951, the requirement of the forces seemed almost fantastic. Speed and altitude unattainable for the production aviation of that time. The team of engineers under the leadership of Robert Widmer turned this fantasy into a flying reality. At the cost of huge expenses, at the cost of several years of uncertainty, at the cost of lost machines and constant work at the limit of the capabilities of metal, electronics, and the human body. The Hustler served in the ranks for less than 10 years, a short period for an aircraft that required so much effort to create. But during this time, it managed to become a real technological laboratory, a test site for solutions that then dispersed to dozens of other programs. The Delta Wing, honeycomb skin panels, escape capsules, electronic autopilot with voice warnings. Each of these solutions appeared precisely here, under the pressure of one bold and almost impossible requirement of 1951. The history of the Hustler is a story of how far engineering thought can go if you set before it a task at the limit of the possible, and that even a short service does not cancel a long technological legacy that continues to live in machines flying in the sky decades after the last Hustler for the last time touched the runway with its wheels. Thank you for watching. See you soon.